In this video I'm going to give you a very brief description of the way blood pressure is normally controlled, and we're going to use that to identify points by which we can interfere pharmacologically. So, if we start with a very simple model of the heart, of the circulatory system, if we imagine that we've got the heart here, and let's really make this incredibly simple. Right? Here's our circulatory system consisting just of the arteries, the capillaries, and veins. I know it's actually a double system. I've missed out the lungs, but this is just to illustrate the point. First thing to realise is that cardiac output, so that's the number of litres per second per minute leaving the heart, is equal to the blood pressure divided by the peripheral resistance. This, of course, is what we're trying to control. So let's redo this. Let's get rid of that and draw it or write it in a different way, in a different form. So blood pressure equals cardiac output times total peripheral resistance. So if cardiac output goes up, TPR stays the same, or if resistance goes up and the output stays the same, blood pressure will increase. So we're going to assume then that we have a homeostatic mechanism working to keep blood pressure the same. And we can do that by changing the cardiac output or changing the total peripheral resistance. Let's look at the first one of those, and we're going to add the central nervous system and the autonomic nervous system. So the autonomic nervous system then, through adrenaline receptors, will increase the force and the rate of contraction. Baroreceptors in the arteries detect increases in blood pressure and then, through this loop, cause a change in the contractility of the heart. So that's us changing the cardiac output. So that's how the nervous system, the autonomic nervous system, plays its part in controlling the blood pressure through changing cardiac output. It does more than that, which I'll show you in just a minute. But there's another player we need to take into account, and that is the kidney. When the blood pressure falls, the arterial blood pressure falls, this is picked up by the kidney, and the kidney releases renin. Renin causes the conversion of angiotensinogen to angiotensin 1. Angiotensin 1 is converted by angiotensin converting enzyme to angiotensin 2. Now from this stage a number of things happen. First of all, angiotensin 2 acts on angiotensin receptors causing vasoconstriction. And that of course results in an increase in blood pressure. So a fall in blood pressure through this loop results in a rise in blood pressure. So we have this homeostatic mechanism taking place. So move myself up out of the way so you can see what I'm talking about there. But angiotensin has other effects too, because the angiotensin 2, also activates aldosterone, so you find all this in more detail in the textbooks. I'm just giving an overview so you can see how the whole system works, enough for you to be able to work out the physiology, the pharmacology. Aldosterone causes an increase in sodium reabsorption, and that causes an increase in blood volume because of the sodium is reabsorbed, water is reabsorbed with it, and that causes an increase in blood pressure. So we wanted to achieve this and this in response to a fall in blood pressure. So you can see there's quite a few points there at which we could show, quite a few points of potential control there, and all of them are exploited. So if I show you in this diagram here from Rangan down, you can see the wall of the central nervous system. So arterial pressure is the result of peripheral resistance and cardiac output. Arterial pressure is detected by baroreceptors in the brain, which responds by, first of all, causing vasoconstriction, causing increase in heart rate and force of contraction, but also interfaces with the renal system. So we've got the central nervous system part here, acting as a negative feedback loop. We also have the peripheral. So this is very short term. This is how it responds within seconds. The kidney system is longer term, and it responds through the renin, angiotensin, and aldosterone pathways, and they work to restore blood pressure. But we have this interface with the central nervous system as well. So now let's bring the central nervous system back into the story again. Remember, we said that it responds by causing the heart rate and force to increase, but it also interfaces with this other green system, this slower kidney system, because what it does is it's getting quite complicated now, it increases the release of renin. It also directly causes vasoconstriction. And so the two systems work together.